Hi, my name is Calvin, and today my thesis project is the design and evaluation of a prosthetic knee joint-based automatic stem face lock technology for children with transfemoral amputations. So, transfemoral amputation is also known as the above-knee amputations, in which the amputations occur in the thigh. So, one of the challenges one of the reasons why above-knee amputations offer more challenges than amputation in the calf or the legs or the foot is because the loss of a knee joint. A knee joint is one of the most complex joints in our body, in which it helps the legs to extend and flexes, at the same time facilitate walking while providing stability. At the same time, this is the reason why it's very important to provide a good prosthesis for people to have a missing limb and restore the function of that missing limb. And perhaps it's more important for children to have a good prosthesis because it not only helping them in their daily lives, but also help them to have a more normal physical and psychological development. And studies have shown that up to 95% of the children who are fitted with an appropriate prosthesis become functional walkers, and most of them actually are actively engaged in physical and recreational activities with their peers. So lower limb amputees faces different challenges, and they often exhibit modified gait patterns because of the missing limb. And other than that, especially for unilateral amputees, they also have the asymmetrical profiles between their prosthetic limb and their intact limb. At the same time, because of amputations, they also exhibit a slower walking speed than able-bodied individual. And because of that, they also have a higher energy expenditure on walking. Now, besides that, amputation also have a significant impact on a child's psychological development because of their inability to engage in physical activities with their peers or family, as physical activities has a significant impact on their emotional, physical, and social well-being. And besides that, lastly, even though they're fitted with prosthesis, there always are fears of falls or the feelings of instability because if the prosthesis is not fitted, it's not well designed, or it's not a good fit for them. So here's the diagram for a gait cycle. Gait cycle can be divided in two phases, which is stand phase and swing phase. So stand phase start with heel strike, which is foot strike, and swing phase start with toe off. So for a prosthetic knee joint, they actually offer two different functions, which is the stand phase control and swing phase control. So for stand phase control, is to maintain the leg from buckling when the limb is loading when the leg is loaded during weight acceptance. And it's extremely important to have a great stem face stability is because when your knee and your planted foot is loaded and then allowing your other legs to swing forward, it's important that it remain extended to prevent fall. And the most common way to achieve such event is to have the most common way of doing that is by mechanical lock or having a polycentric mechanism. And for swing phase control, it is to simulate the action of the leg muscles, which help gait by controlling the duration of the swing. At the same time, it will also help the leg to return back to the extensive position before entering to the stand phase, where the leg is going to accept weight again. So in some high-end design, they often uses the fluid-based mechanism, which is the hydraulic system or a pneumatic system. Although they're able to provide a better, a smoother gait, and also able to adapt to different walking speed, it is very, very expensive and also high maintenance. So for our design, we actually go with a spring design, just because it's more robust and inexpensive, and functionally, it is more than adequate for low-level activity users or mid-level activity users, which will be shown later. So the automatic stand phase technology is what we use for a design, and it's actually developed at the Propel Lab at Hollenberg Kids Rehab Hospital. And throughout the years, different knee joints have been using this technology and have been developed for testing and research purposes. So how does it work? So the automatic stand face lock technology actually work by two different things. First, it relies on the alignment of the knee axis and the control axis, and also rely on the location of the ground reaction force factor. So when the ground reaction force factor is located behind the control axis, which during heel strike, it would create a forward moment, and then allow the lock to be engaged and preventing the knee from bending. But then when you roll your leg over, and when the ground reaction force factor is located in front of the control axis, in this case, it would create a backward moment, which then pushing the lock back, allowing the lock to be disengaged, and allowing the knee to bend and entering swing face. So the reason why we're using the automatic stand face technology is because it is a proven technology. It's proved to be stable and reliable. So in a study conducted in 2005, when we asking participants to compare their conventional knee, their own knee, to the ASPL knee, it has been reported that the rate of falls or the rate of the knee giving out on them has been dramatically decreased when they were using the ASPL knee, which the number goes from once a day to once a month. So at the same time, the ASPL knee actually gives them more confidence when they're walking, and they prefer to continue to use the ASPL knee other than the conventional knee. And in the study in 2007-2011, it shows that both indicated that participants with a unilateral amputation actually generally have a greater walking speed using the ASPL knee than their conventional knee, and without having provide a greater muscular effort, which means it doesn't have to increase the energy expenditure. So these things actually prove that the design can address the problem of the fears of fall or the problem of feelings instability. At the same time, it's also proved that it's stable and highly functional. So the objective from my project is to design and evaluate a pediatric prosthetic knee using the novel ASPL mechanism, as well as incorporating the variable swing face control and extension assist. And after that, we're going to conduct the structural testing and single subject pilot study. So, and here's the proposed method for my project. And so the project can be divided into 3 different stages, which is design and prototyping, structural testing, as well as single subject pilot study. So we have just recently completed the design and prototyping phase where the knee joint is actually being made, and we're going to move into stage 2 and stage 3 very soon to test it out. So what are the design challenges when we're in stage 1? So the design challenge is actually trying to incorporate all the design criteria listed here. We're trying to incorporate the ASPL technology for stand face control, incorporate all the friction control and extension assist for swing face control. At the same time, trying to keep the knee to be lightweight, compacted, and at the same time structurally sound. And the reason why we think that is very important to have all of these features is because in the market right now, a lot of commercially available products often neglect the incorporation of the swing face control and extension assist. And these decisions actually affect the gait characteristics of the users, such as the toe clearance and energy expenditure. So we feel that it's very important to have all these features that exist in the adult knee and also provide them in the prosthetic, in the pediatric knee, even though there's a size constraint. So after the design has been done or the computer model has been created, we also go through the finite element analysis, in which it's actually following the ISO standard for structural testing of the lower limb prosthesis. So in the ISO testing, there's actually 2 different loading conditions, as well as the knee lock test, which is specifically for a mechanical knee-based, knee lock-based knee joint design. So after all the testing or optimization, the knee right now can actually support a 60 kilogram weighted users instead of the goal of having 45 kilograms sitting users. Now you can support 60 kilograms, and as the safety factor is actually 5. It's about 5, and in stage 2, we're going to actually put it to test and see whether it's true or not. So, and here's the design overview So perhaps one of the most interesting points is that our design is actually waterproof. And we think that is very important features to have because we want the child to be able to experience different things, to be able to simply go into the beach or going to do water activities with their peers and family. And actually a lot of the knee in the market right now are not waterproof. And as mentioned before, the knee joint incorporates the ASPL technology for stem-based control, as well as incorporating both the mechanical friction control and extension assist for swing-based to provide better swing-based control. At the same time, this knee actually provides at least 147 knee flexion angle, which is very comparable to all the knees in the market. And here's the two videos that demonstrate the prototype. So in the first video, as mentioned before, during heel strike, their load line is actually located behind the control axis, which creates a forward moment which will engage the lock. So at this time, the knee will remain at an extended position. But as you roll your foot over, and now when the load line is located at the from your toe and then in front of the control axis, in this case, you actually push the lock backwards, disengage the lock, and allowing the knee to enter swing face and bend. So that. And in this video, as I actually try to demonstrate the spring extension assist. So in here is you can see that the spring actually can help the knee to return back to the extended position. Oops, sorry. Can actually help the knee to return back to the extended position. And I just want to draw your attention to here. Actually, for the mechanical friction control, there's actually two shim between the top part and the body part, in which it provides friction between the interface. And from on here, there's actually two knobs where it allows the users to be able to tweak it to adjust the friction, where in order to suit their walking styles or walking speed. Oops. So in summary, the objective of this project is to develop and evaluate a pediatric knee that is lightweight, structurally sound, compact, and yet highly functional. And it uses the ASPL technology for swing-face control, and also incorporating the mechanical friction control and extension assist for swing-face control. So there are 3 stages in this project, which is designing, structural testing, and pilot study, and now we've just finished the prototype and ready for testing. So I just want to thanks for all your attention and time. Thank you.
Very interesting work. Do you have observed the resistance of the knee, resistance features during the unlock?
Oh, resistant features during unlock. Oh, so yes. Oh, we guys actually look at it. So how the resistance of the resistance of the knee.
Yeah.
It's actually provided because there's actually a lock spring at the back, which is constantly applying pressure on the lock. So the stiffness of that polymer will be the resistance. So we actually bought in multiple different polymers, and we're gonna test it out when we're putting a child on the test, and we will see which one actually suited to them. Because different users have different weight and different walking, different gait. So we want to make sure that we pick one that will suit them, but we already have different ones for their exchange.
I guess it's a similar question. How do you choose the stiffness of the spring that you put in it?
Oh, the stiffness, yeah. And so actually for the stiffness spring, as you can see here at this picture, this knee is actually also kind of like same as downsizing of the fully functional adult knee. So this knee is actually starting in market. So it seems like arbitrary number, but the knee, since that knee actually support 100 kilogram weighted users, and this knee supported 60 kilogram weighted users. So we kind of took the 60% off that spring and then kind of use that as a guideline to put it for our when we're picking the spring for our pediatric knee. And the reason why we think that is okay because that adult knee have been tested for a long time in the field, and it seems that all the users have been okay walking with it. So we think that it might be okay to just pick that number and stick time is 60%. But at the same time, to accommodate a younger kids, we also have a 40% spring designed into it. So based on how the kids perform, we can also change it as well. Great, thank you.
The next presentation will be given by Emily, senior